Hello, Padres. Welcome back to another physics tutorial. This one is on the theory of special relativity, and we're going to look at two problems, one involving time dilation and one involving length contraction. So let's get started. For this problem, it takes Moops 120 seconds to brush his teeth. He is a very diligent brusher, and we're trying to figure out how long would it take if you observed him while traveling at 60% the speed of light. So we have our equation for time dilation. It is time equals the original time divided by the square root of 1 minus v squared over c squared. So we're going to plug our numbers in. We're going to set this equal to 120, that is the original time. We have the square root of 1 minus, and for the velocity, we're going to put 0.6 c. And the reason we're putting 0.6 c in there is if I wanted to figure out the actual speed of light at that, speed of light we said was 300 million meters per second. So if I wanted to find out what is 60% of that, I would have to multiply 0.6 times 300 million. I need one more set of zeros. 300, oh my gosh, 300 million. This would equal 60%. So instead of writing all of this and putting that into my v, I'm basically doing that. I'm basically plugging that in. I could also multiply that out, and I'd get 180 million to be 60%. So instead of writing 180 million and putting 180 million into my v, I'm just going to use 0.6c, and you'll see why in a second. So this is going to equal 120 over the square root of 1 minus 0.6 squared times c squared over c squared. And now you can see this lovely thing is going to happen where these c squareds are going to cancel, which is great. Okay, so I'm going to get equal to 120 over the square root of 1 minus 0.36. I can keep going. Over the square root of 0.64, which is 120 over 0.8, which equals 150 seconds. So it normally takes him 120 seconds, that we can see at the top. 120 seconds is how it normally takes. It's taking him 150. So that means because it's taking him longer, time is moving slower because it's taking longer to do it. So he'd be brushing in slow motion. So it'd be taking longer to get to the end. All right. One more problem, this one involving length contraction. So this one, Meeps is traveling on a spaceship, traveling at 95% the speed of light. How much would 1 meter be contracted if you observed her while at rest? So our equation for this, our length equals our original length times the same relativistic factor. So we would have L equals 1, that's 1 meter, times the square root of 1 minus, and I'm going to use the same trick as last time. Instead of doing 0.95 times this, which would equal, let me plug it in my calculator real quick, 285 million. So 285 million is 95%. I could plug 285 million. I could plug that into my B. That would totally work. But I'm going to have that big number squared, and then I'll have to plug in 300 million into C and square that. I'm going to get very big numbers. So instead, I'm going to just put 0.95C, which is basically what I had right here. So I'm plugging that's my velocity, into my C. Oh, sorry, my velocity, my V. And so now what I get, 0.95 squared times C squared over C squared. The C's are going to cancel. I'm going to get L equals the square root of 1 minus 0.95 squared, which is 0.9025. And I can plug that in my calculator, and I get 0.31 meters. So as you can see, we're going very close to the speed of light, 95% the speed of light, and our one meter stick, 1 meter in length, would be contracted to 0.31 meters. So it contracts down to almost a third of the original length. All right, hope you found this useful, and have a great day, Padres.